Hello everyone. I am Jahid Hassan from Purdue University, and today I will be presenting our work focusing on providing explanation for machine learning pipelines under data drift. This study is supervised by Dr. Ramila Pradhan. Let's proceed with the contents. So for a specific machine learning task, machine learning pipelines are usually optimized for static training dataset, and frameworks like AutoML, combinatorial approach, and meta-learning tools help select the best sequence of pre-processing components that basically brings the optimal performance to the downstream model. So for example, let's look at the left at this training data. It has fairly balanced distribution of gender and race attributes, and the pre-processing component, as you see, scaling, imputation, and outlier, and their choices has been tuned on this specific distribution that brings the optimal performance to the model. But now imagine in the deployment scenario where the incoming dataset has changed. Let's say it has now more female and Asian individuals than before. So even though the same exact previous pipeline is applied, the model's performance drops significantly. The performance is not optimal anymore because the pre-processing steps like mean imputation and or scaling are optimized for the original data distribution, and this step now introduce bias or incorrect transformation under the new data. And this is a very common phenomenon in the field of machine learning because dataset often faces adverse scenarios and data changes over time. And there are a bunch of studies that address data drift from model centric point of view, but the core issue is the existing works gives no explanation of why this pipeline fails or what could be the modification to make this pipeline pass. So the practitioner is left with a bunch of questions about pipeline, like how vulnerable is the chosen pipeline to different deployment scenarios, or what are the root causes that make this pipeline to fail, or how critical this drift could affect the performance, or finally what are the recommended modification of the pipeline to pass this issue. So here's how addressing this question formalizes our notion of pipeline explanation tailored to the practitioners. And here we summarize our contribution. We formalize the notion of machine learning pipeline explanation. We also provide a vulnerability report for a given machine learning pipeline. We offer a comprehensive assessment of machine learning pipeline under data drift that includes quantification of the different types of vulnerability and robustness, that provides explanation and the intervention suggestion. Now the question comes, how do we compute the vulnerability of the pipeline? So to compute a vulnerability score for a pipeline component pk, we first measure how much the transformed values changes for original and shifted dataset, what we call the sensitivity of preprocessing component pk, and later we measure the distributional dissimilarity between the transformed original and drifted dataset. This is basically the KL divergence. So together they compute the first order changes in the pipeline and the higher order distributional changes in the pipeline components. So we then synthetically generate enrifted scenarios, like we inject missing values or outlier injection, that creates a full vulnerability matrix for different scenarios and for different preprocessing component. By analyzing the vulnerability score in different scenarios, we generate a user-facing explanation. So on the right side, I provided an example how a comprehensive user-facing explanation would look like. So in the user-facing explanation, it includes total vulnerability score. So basically, our vulnerability score calculation provides us a component level vulnerability. To get a vulnerability for a entire pipeline, we compute the aggregated sum of each components that gives us the total vulnerability score, what I am highlighting here. Explanation also includes vulnerability tolerable thresholds. So the way we form vulnerability score, it's always non-negative, and definitely not all the non-negative score indicates drops in performance significantly. So there might be a threshold beyond which the performance drops significantly, but before that it is tolerable and no further modification is needed. So our empirical evaluation and analysis helps us to give such a tolerable threshold for the user. It also includes the performance changes estimation. So given the vulnerability score for n rifted scenarios and corresponding performance changes, we train a regression model that estimates the performance changes due to the drift in deployment scenarios. And in such a estimation can help the practitioners to measure the severity of the drift. Then we also provide the list of most vulnerable components that are responsible for most of the performance changes due to the drift. And finally, our explanation also provide a new suggestion of pipeline that potentially can mitigate the performance drop and can give the nearly optimal performance in an efficient manner. This is the complete architecture of the study. So the upper portion is showing the regular process of the optimization of machine learning pipeline and how it brings the optimal performance to the model. And the red shaded part, the second stage, is showing how do we compute the vulnerability score and how do we process them. We first simulate n rifted scenarios and compute the vulnerability score, generate the vulnerability matrix, and by empirically analyzing and evaluating that from that metric, we identify vulnerability threshold. And in the final stage, the green shaded box is play the role of explanation and recommendation engine. In this part, we provide a robustness report for the practitioners. We estimate the error of the performance, and if needed, we suggest a new sequence of pipelines to the practitioners so that practitioners can take necessary steps to mitigate the issues that arises because of the data drift. And this framework can be used in both pre and post deployment scenarios. In pre-deployment scenario, it able to provide practitioners an assessment of the chosen pipeline, like what could be the potential failure scenarios, how critical the scenarios would be, what is the prevention for that. And in the post deployment scenarios, it could compute the severity of that drift, the performance drops, and the suggestion of the new pipeline based on that scenario. Here we are reporting our preliminary experiment for the workshop. We evaluated our method on two widely used classification dataset, adult income and German credit. But note that this study is not limited to classification task or structured dataset. Our recent experiment showed that it can be also extended to other task and non-structured dataset as well. And for pre-processing steps, we consider imputation with 3 choices, scaling with standard and min max, outlier with 2 choices. We applied 2 types of perturbation, missing value injection and outlier injection. Here we are reporting vulnerability score for adult income dataset for a specific type of perturbation, which is missing value injection, and the row here is indicating the noise level, which is basically the percentage of rows that has been injected. And this column shows the vulnerability score for missing value imputation, and the last column present vulnerability score for scaling. So as we see, when the noise level increases, the vulnerability score is also increases. And another fact is we see the vulnerability score for missing value imputation is greater than the vulnerability score of scaling. It happens because we calculate the vulnerability score right after the specific preprocessing component being applied. So this is the reason we see higher value for missing values, lower value for scaling, but it doesn't mean that missing value imputation is more vulnerable than standardization at this point, because this point are not comparable. So to compare this, we had to go through one step ahead. We had to compute the gradient of each of the vulnerability score. So here the blue line presenting the vulnerability score with respect to the noise level. When the noise level increases, the vulnerability score also increases, indicates a strong correlation between them. And the orange line shows the gradient for each vulnerability points. And by analyzing this gradient, we come up with a threshold. This vertical red line, it means that if the dataset has more than 6% missing values, the model is likely to decline by more than 3%. This 3% is specified by the user. It shows the vulnerability matrix for outlier injection as similar as the missing value injection. It shows the upward trends, although it is fluctuating. Overall, it has a strong correlation with the noise level. The orange line is showing the gradient, implies the changes at each point of vulnerability score, and the vertical red line implies the vulnerability tolerable threshold, means that if the dataset has more than 8% outlier, the performance of the model is likely to decline significantly, but before that point, no further modification is required. It's tolerable. And here is an user-facing explanation from the experiment on real-world dataset. So for a given shifted version of adult income dataset, the vulnerability score is around 6.2, which is greater than the tolerability threshold 4.9. So the performance of original trained model M is likely to decline by 4%, which calculated from the regression model we trained. And for the explanation part, the most vulnerable component was missing value imputation using mean. And for the intervention part, we are on it and we see some potential direction that could lead us to modify the pipeline model, bring the nearly optimal performance without modifying the trained model. So we hope to report it soon. And to conclude, we provide a drift-aware explanation for machine learning pipelines with a lightweight robustness assessment of pipeline under drifted scenarios, and we also provide component level user-facing explanation that helps the user to take necessary steps in adverse scenarios and to fix the pipeline and model performance, and it can also help as a prevention in the pre-deployment scenarios. Thank you. Thank you for listening me. You should have any questions or suggestion, please reach out to me at my email. And also you can scan this code for the technical details and everything. Thank you.